Right. My name is June, and today we're actually going to start learning about action potential. Well, I wrote a lot of things, but it's because that I started this lecture and then I found out that I wasn't recording. So, yeah, let me start to get all over again once. So, okay, let's go. So, the first thing I wanted to talk about is that when sodium has a flux which comes inside, we need to know that it's due to a specific protein channel called the nicotinic acetylcholine receptor. Yeah, it's a long name, and yeah, it doesn't look quite nice, but once you know that each meaning of these nicotinic acetylcholine receptor, then yeah, you can easily find out that we write these things like this. R for referring receptor, ACR for referring acetylcholine, and then N for referring nicotinic. Right. Then what does this strange looking thing do? Is that it triggers depolarization. Well, not specifically that this thing triggers depolarization, but uh, when this kind of protein structure combines with the ACH, then it tends to have a trigger on putting the sodium inside of our cells. So that's how our neurons or our muscular cells kind of develop the state of starting the depolarization of letting the sodium enter its membrane. So once the sodium is inside the neuron cell, for example, just giving an example, it has a trigger effect. And just for a caption of our last lecture, what was it? Yeah, it's depolarization. So yeah, it starts the depolarization by starting the sodium interference with other kind of channels, and we do have to know that the basic voltage that the cell naturally have is given as minus 70 millivolts. I kind of explained this for like 5 minutes on while I was not recording, but yeah, for normally we say that potassium and sodium is kind of interfering with each other, but there's also magnesium, calcium, and chlorine kind of interferes. We'll talk about calcium and chlorines for later channels, but yeah, due to their existence, it kind of remains on minus 70 millivolts. So when it starts, the depolarization, and before the depolarization I told you that the NACR kind of interferes with not sorry ACHR kind of interferes on entering the sodium itself, so that actually tends to kind of put the sodium into the state of minus 50 millivolts difference between the cell and its outer environment. So uh, when the voltage reaches to minus 55 to minus 50 millivolts, a specific channel named VGSC, which, yeah, it very sounds different to other channels when, well, we were talking about sodium channels or sodium or potassium pumps. Then as I mentioned, we're kind of like developing it into a further level. Let's just call this VGSC. It actually refers to voltage gated. What do you think that S stands for? Yeah, you're right, sodium. And then channel. It's a sodium channel. It's the thing that we've studied about, but it's voltage gated, which refers to that it opens and closes in specific voltages, and the specific voltages are minus 50 to minus 50 millivolts. And the point is that they tend to open very quickly. This is very, very important, and you need to kind of emphasize on this. Like, why does it open quickly? Does anybody have an answer? Well, it's because that the key feature of this subunit tends to react very, very, very fast compared to other subunits. We will talk about the VGKC, which stands for voltage gated column channel, I don't know why this is kalium itself. We normally pronounce it as potassium. And like for anyone who doesn't kind of understand what I'm saying right now, the natrium it refers to sodium, and then the kalium refers to potassium. I'm not quite sure if this spelling is correct, but yeah, mind me later if I'm really wrong after my lecture. So this voltage gated kalium channel is composed of 6 subunits. You don't need to memorize it. The 6 subunits consisted of like four, which interferes with the voltage, and then two, which kind of like is stuck in the membrane. But these 4 subunits acts independently in the case of VGKC. So that means that it takes a very, very long time to kind of interact with other things, and it takes about like 3 milliseconds, which is a very, very long time. No, I'm not quite sure if it's 3 milliseconds, but compared to it's about like 1 to 4 milliseconds, if I'm sure. So the VGSC tends to react in 0.1 or 0.2 milliseconds. So compared to this, they have a very, very, very large amount of delay. So after the VGSC is opened, then it kind of goes up. Goes up to which point is about plus 30 millivolts. Right? So I told you previously about the VGKC that it kind of tends to open about 1 or 4 milliseconds later. So being very, very precise, they actually open about like in minus 40 millivolts. Can anybody guess why? It's because that uh, they have our body system kind of has a system that after the sodium, well, VGSC channels tend to close, then the VGKC tends to have open. So they have a very specific, what do you call, system in our body, which kind of maintains each opening of the channels itself. So after the VGKC opens out, it goes way below our normal level, up to minus 80 millivolts. So the reason of this is that like they do interfere slowly, but there's another thing that kind of is involved related to this. So let's talk about this. Right. So now we have to talk about the chlorine interference. I previously talked about like the chlorine is kind of interfered in this areas, and there's a specific protein receptor called the GABA receptors. Maybe some of you heard of it, maybe no. Specifically the GABA A. Let's just draw it like this. Yeah. I'm sorry. I'm sorry. Let's go on. So what the GABA receptor actually do is it's activated by the GABA acid. There's a very long circumstances if you write these things all down, but yeah, I don't remember that too. So I think you guys don't need to remember it. So this thing allows chlorine influx, which is very, very, very important. Let's think about it. So the chlorine has kind of like a negative thing. So when this is the inside of the cell and this is the outside, the voltage is remained due to the difference between the sodium and the potassium itself. But once the chlorine actually gets through and becomes the inside, the voltage of the inside layer has to become very, very low. That's right. Lower than what? Lower than previous state when the cell isn't working at all, which is the minus 70 millivolts. So after the chlorine kind of enters here, it kind of tends to remain in minus 80 millivolts since the chlorine actually has a negative ion charged and it interferes with the voltage difference. And this process is called hyperpolarization. Right. So this state refers to hyperpolarization. After the hyperpolarization, the potassium channels actually start to close, which I refer to the voltage gated potassium channels, and the state of voltage tends to become higher. Oh, sorry for that. So it has to remain in a state of minus 70 millivolts, and it comes back. About the minus 70 millivolts, if we look at the cell cycle of the neuron, it's actually the most of its life is inactivated compared to its activation. So if you think about that, minus 70 millivolts is kind of like a tendency that the cell actually wants to have on its environment. It has to kind of remain. It wants to have the specific kind of environment to kind of cope with everything I just talked about. So it starts on, let's summarize it. The sodium actually enters due to the NACHR, which is the nicotinic acetylcholine receptor. And once the sodium is actually inside the cell, it triggers to minus 55 to a minus 50 millivoltage, which is then used as the VGSC, which refers to voltage gated sodium channels. And then these channels tend to kind of let sodiums inside much more rapidly, and they act very quickly too. So once the voltage is up to minus 40 millivolts, then there's a signal to the VGKC, which refers to voltage gate potassium channels, and they tend to open, but after 1 to 4 milliseconds later. So that's why once they open, it's about like in these areas, not this, not very directly as the NGSC did. So after the potassium enters, the voltage gets rapidly lower due to the exploit of potassium. And there's also the interference of the GABA A receptor, which kind of lets in chlorine, which kind of lowers even more than the voltage difference that the natrium potassium actually used to be. And this process is actually called the hyperpolarization. After the and after the VGKC kind of stops exploiting the potassiums, then it closes and the voltage remains in minus 70 and comes back. And I think that will be the end of the lesson. And today we learned about action potential, and this was June. Thank you.